This next section is quantitative aspects of reactions in aqueous solution. So we have a few things. We already filled in the blank here. So we have quantitative analysis. These are just some definitions. It is the determination of the mass or concentration of a substance in a sample. We have qualitative analysis, is the determination of types of ions present in a solution. We have gravimetric analysis, which is an experimental procedure based on the measurement of mass. And we have precipitation analysis, which is finding the composition of a component of a compound by depositing it from a solution as an insoluble compound called a precipitate. PPT is not PowerPoint, precipitate. And we'll actually do a precipitation analysis for the very last problem. So quantitative analysis example. So if I wanted you to determine the percent by mass of chloride in a sample, what you do is you weigh the sample, you dissolve it in distilled water. Why distilled water? Again, you don't want any impurities. You would add enough silver nitrate of the known concentration to form a precipitate of the chloride. Because remember the solubility rules, silver is going to pull out chloride. And I could, there's other things I could use, but again, it's just silver. I could use lead too as well. So we're using silver. So silver chloride precipitate is separated from the mixture by filtration and then is dried and weighed. And the amount of the chloride determines the amount of silver chloride. From the amount of silver chloride, you're going to determine the amount of chloride present, and we do that by doing a percent by mass of chloride original sample. So we take the mass of chloride divided by the mass of the sample times 100. And then we have all the solubility rules. You need to know the solubility rules. I've expanded the solubility rules here. So one example of knowing your solubility rules, I could ask you, how could you precipitate out lead 2 or plumbous iodide? And so I want to form lead, and I have to get lead and iodide into solution first of all. So with the iodide, I can add I'm looking for a cation, so any alkali metal is good. So I use sodium to get that in. For my lead to get in, I need an anion, and nitrate's always good for that. When I get those in, they will actually dissolve out. And that's only one option. There's other options based upon the rules. Secondly, part 2 is if I wanted to get manganese hydroxide or manganese 2 hydroxide out of solution. So get manganese in solution. A great way to do that is using nitrate again, a very easy one to use. To get hydroxide in, all I have to do again, remember, is add it with any alkali metal. Well, hydroxide is commonly insoluble except with alkali metal, so any alkali metal will get that in for me. So these are just options. That doesn't mean this is the only way to do it. There's other options based upon your solubility rules. Then I could give you another example where I said now I give you 3 cations. So now we have to figure out what anions do we need to mix in solution that are going to pull these cations out of solution. So first of all, I'm going to go after silver. I'm going to add chloride in. When I add chloride in, that will pull the silver out. Now I have copper and barium. So then I'll add sulfate in. Sulfate's going to specifically go after the barium. And then I have remaining my copper. And with my copper, I can really add almost any of my anions there. The hydroxide will pull it out. I have carbonate, phosphate, sulfide, and others will actually pull it out of solution. So again, these are just ways of doing it. This could be done in the lab activity. But again, just make sure you know your solubility rules, because I could ask you something like this on the test. Let's move into another example. And this example kind of has multiple questions within it, and these actually can be pulled out as separate little problems here. So it's very important you understand the whole idea here as you go through it. Very, very important problem. Make sure you know it. Again, hint, make sure you know it. So in a lab, a student forms 5.34 grams of silver chloride precipitate by reacting 1.755 grams of an unknown chloride sample, that's your solution, with an excess silver nitrate solution. So we did this, we get our overall solution, and it says we have to write the net ionic equation. Well, the net ionic is all based upon the precipitate. If you remember that back to our double displacement, from the precipitate we go backwards, we have the cation and anion to make it up. Well, our precipitate was silver chloride, so the cation is silver and the anion is chloride. That's your net ionic. So once you know the precipitate, just break it apart. Well, now I want to calculate a percent by mass of my chloride. So in this situation, I need to know the mass of my chloride. All I know is the mass of my silver chloride. But I knew I can go a molar mass, get the moles of silver chloride, and then like we've done before, we can go to a mole-to-mole ratio within the compound. For every 1 mole of silver chloride, there's 1 mole of chloride. And then you use a molar mass of chloride to get the actual grams of chloride. but it's percent by mass. So I need my grams of chloride divided by my grams of solution, which were 1.775. And that would tell me my percent chloride in the solution. Next, we've done a problem like this before. This is a great problem. Well, now the formula is XCl2. What's your X? And so what we need to actually get is we need to get its molar mass. We're going to use the periodic table to go backwards. Now, instead of using a periodic table to get the molar mass, we're going to get the molar mass and go back in and use it to identify the element. So in this situation, we need what I know about my X. If I'm going to use its molar mass, I need its grams, I need its moles. So first of all, I know that I've at 1.32 grams of chloride. I get my molar mass, and then I can go from 2 moles of chloride to every 1 mole of X, doing a mole-to-mole ratio within the compound that gives me moles of X. To get its mass, I do know of my mass, of my 1.775 grams, my total mass, my unknown sample, of the unknown chloride sample, 1.32 of that is chloride. That means the rest of it is my unknown, which I'm going after. So I know its mass and I know its moles. Grams per mole gives me molar mass, and that molar mass ends up being 24.44 grams per mole, which is very close to magnesium. So it would be magnesium chloride. Also, to check my work, I know I needed 2 chlorides to zero it out, so I know I had to be dealing with something with a +2 charge. Another example, a student mixes now 125 milliliters of a 0.124 molarity aluminum nitrate and 175 molarity of a 0.104 molarity barium chloride. One thing that's always important to understand here when we go after this, when you're mixing solutions, pay attention. You now have a new volume, so really pay attention to that as well. So right away I see 125 and 175, I realize I have a new volume of 300 milliliters. So that's going to come back up in a second. But first of all, I want you to write the molecular, ionic, and the net ionic for this. And so this is a great example. So you have to know the reaction. I identify it's a double displacement. I balance it. I do know that my solids, according to my solubility rules, and you have to know this, your aluminum hydroxide is your solid, that's your precipitate. So right away I know that the other compound, the barium and the nitrate, are my spectators. So once I get rid of my spectators, I do know that then my aluminum and my hydroxide are the 2. So it's a 262, which is a 131. Now in this situation, I want to know the moles of my silver, of my aluminum nitrate. I want to know the moles of my barium nitrate. As we go on, the reason why I'm doing this right now is I'm going to go on in a second, part B, and we're going to go after the theoretical yield. And I have to figure out who the limiting reagent is with doing that. But I can actually do that by converting to both the moles. So I actually use its molarity. I know its volume, I know its molarity, and I got moles of my aluminum nitrate, and I can get moles of my barium hydroxide doing the same way. And we're going to use these, and it's just actually right now as we move on. So I always get this information. Now part B, I want to know the mass of precipitate formed. Well, the mass of my precipitate formed, I'm looking again, going back. I realize my precipitate, who I'm talking about aluminum hydroxide. So who's my limiting reagent? Is it aluminum nitrate or is it barium hydroxide? Well, I've already got you halfway there to moles, so now you just have to get moles to your theoretical yield and compare them. As we actually convert them both to aluminum hydroxide, we realize the lower amount is your 0.947. That is your theoretical yield. Therefore, barium hydroxide is your limiting reagent. So I figured out, again, the mass of my precipitate form, theoretical yield. I've also determined my limiting reagent. Now my limiting reagent becomes important because I want to know now the concentration of my excess cation. Well, I do the same mole-to-mole ratio now going from my limiting reagent to my excess reagent. You actually do this in your homework as well. So I figure out my moles of my aluminum nitrate. That's my excess reagent. That's how much actually reacted. Where I knew I started out with 0.0155 moles of it, subtract out what I used, and I realized then that I actually had 0.0034 moles of aluminum nitrate remaining. Now when I want moles, I want concentration. That means moles per liter. Where you go back, you remember we added 2 solutions together, correct? 125 mils and 175 mils. So we have 300 mils or 0.3 liters. So I figure out the concentration of my aluminum nitrate. But then I go back to the problem and realize I'm not done because I don't want to know the concentration of my excess reagent. I want to know the concentration of my excess cation within my excess reagent. So I'm actually going after aluminum. And as we recognize here, you realize for every 1 mole of aluminum nitrate, there's 1 mole of aluminum. Therefore, they are numerically the same. But we got it all the way down to the concentration of the excess cation. Great question. Better know it. The next question says the student wants to determine the molarity and percent by mass of sodium chloride solution. So the student slowly adds 0.1 molarity of silver nitrate until he observes that no more precipitate forms. He had added 12.45 milliliters of silver nitrate to 100 milliliters of a sodium chloride solution. And the specific gravity of the sodium chloride solution is important. When we're talking about of the sodium chloride solution, I provide that specific gravity for you. So basically, I've given you density. But first of all, I want to know what is the molarity of my sodium chloride solution. So again, first of all, I need my double displacement reaction. It's a 1:1:1 ratio. Now, I don't know the molarity of my sodium chloride. That's what I'm going after. I do know I have 100 milliliters. For my silver nitrate, I do know its molarity, and I do know the volume I use. So if I know its volume, I know molarity, guess what? I can figure its moles. Now pay attention here. This is really quick. If my silver chloride and my sodium chloride and silver nitrate are a 1:1 ratio, that means and we're going to assume this is completely reacted. Therefore, they are a mole to what's a 1:1 ratio. Therefore, their moles are the same. So in this situation, since I know the mole, I can actually see this in the problem. I already see that what I speculated, since it's 1 mole of sodium chloride to every 1 mole of silver nitrate, they both have the exact same number of moles. So since I knew the moles of my silver nitrate, I also knew the moles of my sodium chloride. Therefore, I just have to divide it by its volume in liters, moles per volume, and I got its actual molarity of my sodium chloride. And so there's my moles. And I see, so you can actually see they are numerically the same. So I didn't even have to do the mole to mole ratio for my silver nitrate to sodium chloride. I already knew they would be numerically the same because in the balanced chemical equation, they are a 1:1 ratio. Well, part 2 goes, now I want to know the percent by mass of the sodium chloride solution. And we're talking about my 100 mils here. This is important, very important to understand this. So I'm not dealing with the additive that was added in. I'm just focusing on the sodium chloride. So I have my grams of sodium chloride per my grams, my solution. So I need to get grams of sodium chloride. Well, I know it's moles times its molar mass gave me its mass, and then divided by the mass of solution. Well, I know I have 100 milliliters of solution, which is therefore equal to 100 grams of sodium chloride solution. We're talking only about the sodium chloride. And therefore, the percent sodium chloride is a 0.0728%.